Hi, welcome back to Imperium Learning. I'm just going to quickly show you how to estimate an arch model on Eviews. So let's just, oh, I've already done it. Okay, so I'm just going to click on Quick. I'm going to click on Estimate Equation. And then straight away underneath the estimation settings, look at the method. It says least squares, but we don't want that. So we're going to go on the drop down menu and we're going to click on Arch. So this opens up a completely different equation estimation box. Now bear in mind that the default setting is set to a Garch 1-1 model. We don't want that right now. We're getting a bit ahead of ourselves, so we want to turn that to a 0. Right, so an Arch 1 model has a 1 there. If, however, we wanted to do an Arch 2 model, where the conditional variance would look like this, then we would go in here and we would type 2. If we wanted an arch model, an arch 4 model, where the conditional variance looks like that, we would go in here and we would type in 4. But for now, we're just doing a 1. Okay. For our conditional mean equation, we're just going to be typing in our dependent variable, followed by our armor model that we've chosen in a previous step. So in my case, it's an armor 4-2 model. And so as you can see, make sure you've got all your observations in your sample range. Go to options. Now, the optimization method is a bit wrong, unfortunately, the default setting. So you have to go click on it and click on Eviews Legacy. I don't know why it is like that, but you just do that. And then you click OK. And you've got your equation output box right here. Now it's quite good to see that most of the variables are still significant at the 5% level, albeit straight away 2 of them are not significant. Don't worry about that. And also, when we estimate future Garch models, which we'll be doing after we've estimated an arch model, you'll find that the variables for your conditional mean equation are going to become less and less significant. So in other words, by the time you're estimating asymmetric Garch models, you're probably going to find that most of your variables in your conditional mean equation have p-values which are above 0.05. That doesn't mean that you have to drop them out, by the way. Just keep it like that, even if most of them are insignificant. But anyway, our main focus now is on the variance equation. As you can see, we estimated an arch 1 model, so our conditional variance equation looks like that. Okay, and so the resid, open brackets, minus 1 to the squared to the power of 2, that's what this term here is. And so the coefficient alpha 1 equals 0.420157. Okay, so that's our arch term right there. Now that's good to see. It satisfies the non-negativity restraint, that's what it's called. And you can see from that bullet point there, it says it should be noted that alpha 1 has to be positive, since sigma squared t itself and u squared t minus 1 has to be positive since they are squared terms. So that's all good. And as you can see, it has a p-value which is significant at the 5%. This is what you should really be focusing on. You shouldn't really be analysing the constant very much. Just make sure that it's above 0. And but your main focus should be on this term here in the variance equation box, just to say that the coefficient itself is significant and that it's positive. That's all you really need to say for it. And then so we can conclude that the previous lag, the squared error term in the previous time period, is significant in explaining the variance of the error term in the current time period. So that's all you really need to talk about. And then so just moving on, straight away we have to do our residual tests again. We should be doing the Lumbox test for autocorrelation, and then we have to do the ArchLM test, see if there are arch effects present in the residuals. So yeah, let's just do that very quickly. I've already done this in a previous video where I've sort of explained the residual test, so if you haven't seen that yet, go and give that a look. But I'm just assuming that everyone's seen it. So straight away I'm going to do the Lumbox test, and straight away we can see that it suffers from autocorrelation. Notice that. All the p-values are below 0.05. So that's got some issues for us. That presents some issues for us. And then let's quickly conduct the ArchLM test. Again, like I said in a previous video, you have to calculate the optimum lag length for the arch test. And you'll normally do that by minimizing an information criterion. Mine, I always just choose the Schwartz information criterion, so there's my value there. I just want to check which lag length actually does minimize the Schwartz information criterion. Yeah, so I've just done it on an Excel spreadsheet, and it shows that the arch, when we're doing the arch test, the best number of lags to choose that minimizes it is the six lags. So let's just do that very quickly on Eviews. Just show you very quickly. Notice, by the way, that when we only this is only for one lag for the arch test. Notice that it actually rejects, or sorry, it's unable to reject the null hypothesis that there are no arch effects. So if you were using that with just one lag for your arch test, you would conclude that there are no arch effects. But if we go down to view, we go down to residual diagnostics, we click on ArchLM test, and we type in 6. There you go, you've now got 6 lags. You can see, and this is our Schwartz information criterion right there, 5.191148. Let's just check that. 5.1, yeah. And so as you can see there, and again, look at the second row, you can see that the p-value is 0.000. So that means we can reject the null hypothesis at the 5% level, that there are no arch effects. And so as a result, we need to think about we need to be thinking about additional models. Now, bear in mind that this might be a chance to specify an arch model of a higher order. So, you know, we might want to estimate an arch 5 model. Now, an arch 5 model, bear in mind, would have a much longer conditional variance equation. That's the only difference between an arch 1 and an arch 5 model. The conditional mean equation is the same. The variance equation, though, is different. It would probably be unwise, though, to estimate an arch model of a significantly higher order, because it wouldn't be parsimonious. I'm actually probably going to create a new video now, because I'm approaching the 10-minute mark, just explaining why we should only do an arch 1 model and not of a higher order. Okay, bye.